Continuing in quantum and nuclear physics, we're now going to talk a little bit more about quantum theory and energy levels at the atomic level. In chemistry, you may have done a spectroscopy lab where you took a gas, ran a charge through it, and looked at it through a spectroscope, and you were able to see the different spectral lines that were being emitted by that particular gas, something like neon or argon, one of our inert gases, and you put it in that box, plugged it in, and it started to glow. It looked kind of like a neon sign, and when you looked through it using that spectroscope, it actually broke up into different specific lines that had different specific colors following the color spectrum. And depending on what gas you were looking at, it had different spectral lines. This is called an emission spectrum of an element, and it's related to the amount of energy that's being released as electrons move up and down between energy levels. If we look at this diagram below, it actually shows the emission spectra for a number of different elements. The very first one, the one that looks almost just like a picture of the visible light spectrum, is actually the sun. And if you look very carefully, there are a very few distinct places where there are black lines. The areas where there are black lines show specific wavelengths that are not emitted by the sun. You can see that it actually emits almost the entire range of visible light. If we look below, we have hydrogen, and you see hydrogen has some at the red, a little down here at the blue, and then further on in the purple range. And so those are distinct amounts of energy that are being released by that particular element when the electrons are excited. And looking down as we go, helium, mercury, and then at the bottom you have uranium, the more spectral lines, the more lines in the emission spectrum, the more possible energy changes that an electron can experience as it moves up and down between energy levels in an atom. Now, in addition to emission spectra that we see when gases are excited, whether by excessive heat or electricity, we can also get what we call absorption spectra. And absorption spectra are actually the inverse of emission spectra. They are the wavelengths of light that are absorbed when electromagnetic radiation is shown upon a gas, upon the atoms in a gas. And if we were to compare the absorption and emission spectra for something like helium or hydrogen, we would actually see that the areas where the bright lines were for the emission spectrum were identical to the areas where there were dark lines for the absorption spectrum. Now, one thing that's interesting to note is the absorption spectrum for the sun. And if we look at a very detailed example of the absorption spectrum, you should be able to see that there are a very wide range of frequencies in which the sun absorbs energy. It absorbs energy across the entire range of the visible light spectrum. Everywhere on this particular diagram where you see a black line, that's a place where, or that's a specific frequency where the sun is absorbing energy. Now, the thing that's most interesting about these spectra, both the emission and the absorption, is that those bands occur at very specific frequencies. It's not a gradual increase of brightness, it's not a range. For the most part, they're very distinct lines that occur at very distinct frequencies. And those change depending on the gas, and they're actually one way that scientists are able to identify gases. And this is actually how scientists first identified the element helium, and it was first identified on the sun. Scientists looked at the absorption spectrum of the sun and saw particular dark lines, and that told them that there must be some other element up there that they didn't know about. Now, one of the first people that tried to explain this was a Swiss physicist named Johann Balmer back in 1885. And as he did some trial and error, some experimentation, he was able to derive an equation for the emission spectrum of hydrogen. You can see this equation there. This is not an equation you actually need to know. This is just what he happened to actually derive. And in this equation, R was a constant value, and n was a whole number integer, 1, 2, 3, 4, 5, and on up based on the spectral lines. Now, this ended up being an incorrect equation, but it led to the further explanation of the atomic spectrum and the idea that the light, that electromagnetic radiation that's being emitted, must carry energy. And if it carries energy, then it must be equal to the difference between the total energy before and after the emission. And so if we consider the electromagnetic energy being released, that energy had to come from somewhere, and it probably came from inside the atom. And so the atom must have had more energy beforehand and less energy afterwards, and the difference correlates to the wavelength of the photon of light that was emitted, and that's what we see as the emission spectrum. And since the light consists of photons of a specific wavelength, then they must have some specific amount of energy, which is given by our equation E equals hf. And again, as we derived before, F is c over lambda, and so we can say the energy in the photon is h, Planck's constant, times the speed of light divided by the wavelength of that particular light. So what this tells us then is that the energy in the atom is discrete. It's not a continuous range of energy. It has discrete specific values as shown by the discrete specific wavelengths of light that are emitted. Now, another way that scientists attempted to explain this phenomenon was what we call the electron in a box model. And we start with the idea that if the energy of the atom were continuous, then the emission of the light wouldn't always be at these specific wavelengths as they were observed. So let's say we have a sample of hydrogen gas. It doesn't matter where that sample is, where it was collected. If it's hydrogen, if you excite those electrons, you are going to get the exact same emission spectrum no matter what. If the energy in the atom was continuous, that's not necessarily so. You would get a range of wavelengths. You wouldn't always get the exact same emission spectrum. The electron in a box model was one of the first ways to try and explain this idea. So let's imagine that the electron is confined inside of a box that has some length that we're going to call L. And let's, for simplicity's sake, imagine that it's just a one-dimensional box, and that's what we have here. And somewhere along this line here, we're going to find our electron, somewhere between a point x equals 0 and x equals L, which is the length of the box. If the electron is treated as a wave, we've addressed that particles can have wave functions and waves can have particle-like behavior, then the wavelength of that electron is going to be given by h over p. H is Planck's constant, p is the momentum of the particle. And so if our electron is treated as a wave, the magnitude of the wave at 0 and at L is going to be 0. And so these are what we call nodes of a wave. The displacement of the wave at those 2 points is going to be 0. And in this box, it's going to be what we call a standing wave. So it's going to oscillate back and forth within here. Here we have our nodes. Node 1, node 2. And so this then tells us that the wavelength must be somehow tied to the length of the box. And the equation that relates it is lambda equals 2L over n, where n is again some whole number integer. And basically what it means is that the electron can have specific discrete wavelengths, the smallest of which is equal to twice the length of our box, because the smallest amount of a wave that could fit in this box and meet these parameters is a half a wavelength. That would give us a node at either end and what we call an antinode in the middle. And so this right here is half a wavelength. A full wavelength would be twice the length of our so-called box. And then the next wavelength that would be in there, or the next wave function, would be the length of the box, or full wavelength would be the length of the box, because we now again still have a node here and a node here, but we have two antinodes. And so there's a relationship between the length of the box and the wavelength that we can see there. So we can use that relationship to calculate a momentum for the electron. And based on the wave function, momentum is Planck's constant divided by wavelength. In our electron in a box model, the wavelength is given by 2L over n. A little bit of rearrangement, and we get Planck's constant times that whole number coefficient n divided by 2 times the length of the box. So this is the momentum. This is the momentum of the electron. If we have momentum, then we can find the energy associated with that particular electron. And our energy equation, the kinetic energy of our electron, is given by the momentum squared divided by 2 times the mass of the particle, and in this case the mass of the particle is of course the mass of an electron. But we're going to substitute in momentum for the equation that we just derived, hn over 2L, and so we plug that in here, we distribute through, and we get an equation for the kinetic energy that is equal to n squared times Planck's constant squared divided by 8mL squared. Now, because we treated the electron like a standing wave, that meant that there were those discrete wavelengths that were available. There was 2L, there was L over 2, so on and so forth, which is where the idea of these discrete energy amounts came from. So depending on the wavelength of the electron and those discrete values based on the length of the box, those gave us discrete amounts of kinetic energy that the electron could have. Based on this equation, there were only specific amounts of energy that any electron in an atom could have based on the length of that box. And so it helped to kind of fit in that idea of discrete energy levels, even though it was eventually shown to be inaccurate. Now, a number of years later, a scientist came along named Erwin Schrödinger, and Schrödinger came up with a much more accurate quantum model for the behavior of electrons in atoms. And Schrödinger, just like de Broglie, assumed that there was some specific wave function that was associated with particles, and specifically electrons. And that wave function was given by this funny looking function down here. And essentially, psi, that's this Greek letter here, is our wave function, and it's a function of position and time. And so waves are one of those quantities that is affected by two components. We can look at it at any position, we can look at it at any time and get results. And so that actually makes it obviously more difficult to solve an equation related to waves, but Schrödinger was an excellent mathematician and was able to come up with the Schrödinger wave equation. You do not need to know this equation. It is certainly one of the more difficult equations in physics. You don't have to worry about it. Just understand that it exists, that there is an equation that can be solved to find the function of the wave's position. And after Schrödinger, along came Max Born, who was a German physicist, and he suggested that the equation you see here, which is basically the square of that function, can be used to find the probability of finding an electron near any position at any time. So if you're looking at some given position at a given time, you can calculate the probability of finding the electron at that point. Or the significance of this is that it's a probability, which means that you don't know exactly where the electron is. Based on this equation, you can't tell specifically where an electron is at any given point. You can find the probability of its position, but never its exact position. And this was a huge divergence from what physics had been up to that point. Based on all classical physics calculations, you could find very exact, detailed information on particles' positions, on their speeds, on their direction, on basically anything and everything about it, given enough measurements. So the more measurement you had, the more precise position velocity, etc., that you could find about that object. At the quantum level, this suddenly became something that was not possible to do. But when Schrödinger's theory, when his wave function was applied to electrons, it did give very similar results to the electron in a box model, but they were much more accurate. And it predicts the total amount of energy in an electron. And this value C, this capital C, was a constant that was equal to this big long equation down here, which when calculated gave you a value of negative 2.179 times 10 to the negative 18th joules, or 13.6 electron volts. And so the energy of an electron was equal to negative 13.6 divided by n squared, which was the quantum number, that whole number coefficient. So again, with much more precision, this equation, this idea, predicted that there were specific discrete amounts of energy, or quantized energy, that the electron in a hydrogen atom could have. It also predicted the change in energy that would happen if an electron in a hydrogen atom went from a higher energy level to a lower energy level, and in that process emitted a photon. It predicted the energy of that photon. So, knowing that the energy of a photon is given by HF, and knowing the energy level difference, we can calculate the frequency and wavelength of a photon that gets emitted between any transition that an electron could undergo between energy levels. It also allowed us to predict the probability that a particular transition would occur. If you look at an emission spectrum, you'll see that some lines are brighter than others, and this is because the probability of that specific transition between energy levels is much higher, or is higher than another. So the dimmer spectral lines have a lower probability of occurrence than the brighter ones, and so they happen less frequently. The Schrödinger theory did a very good job explaining atomic spectra.